All right. So we just got done graphing the reciprocal function. Here's the homework that you did. Reciprocal function looks like this. And next we're going to talk about some more, I guess, complex types of reciprocal functions. And we'll just call them rational functions. Now, they do end up looking very similar to the reciprocal function, just a little more complex than that. But the difference between a straight up rational function and the reciprocal function is that a rational function is a fraction, first of all, that has a polynomial in the top of the fraction and a polynomial in the bottom. So we're talking about p of x. This is a polynomial. We're not saying p times x. And this is q of x. We're not saying q times x here. All we're saying is, hey, p of x and q of x, those are polynomials. With a condition, right? Since we can't divide by 0, well, this q of x polynomial down here can't equal 0, right? So whatever you plug in for x, it better not equal 0, because that's not part of the domain. Anyways, how do you graph? Well, the way that you graph is you're going to get a rational function like this. Let me show you an example first, okay? Yeah, all right, how about this first example? Now, this is a polynomial rational function, right? We got a polynomial x minus 4 over x plus 4. And so step one, you need to simplify. Now, this one's already simplified. There's nothing to factor and cancel, right? And so that step one's already accomplished. Step two, you need to find the x-intercept. Well, how do you find the x-intercept? You do that by setting the numerator equal to 0, and I'll show you why. The x-intercept, look here, this point here is where the graph crosses the y-axis. Now, that is the x-intercept. And the value of an x-intercept is always 0. The value of the x-intercept, I'm sorry, I'm talking y-intercept. Here's the x-intercept, I'm sorry. So here's the x-intercept right here on the x-axis. Sorry about that. All right, x-intercept. The value of the x-intercept is when y equals 0. Sorry. So we need to find the value that makes the function equal 0. Well, how do we figure that out? Well, you can't divide by 0, but you can divide 0. And so, long story short, you can have 0 on the top, you can't have 0 on the bottom of a fraction. And so to find the x-intercept, we need to figure out a value for x that makes this fraction equal 0. Well, if the numerator equals 0, then the fraction equals 0, which makes the y value equal 0. And so what you need to do is, to find the x-intercept, you need to set the numerator equal to 0 and solve for x. So here we go, x-intercept. Here's the numerator, x minus 4. We set it equal to 0, and we solve. So when x equals 4, you get 4 minus 4, which is 0, making the function equal 0. And so the x-intercept is when x is 4. All right, x-intercept when x is 4, y is 0. Now, that's an accurate point that we can find on this function every time, or this graph every time. And that's the first one you should find. Next, you need to find the vertical asymptote by setting the denominator equal to 0. And so here, the vertical asymptote represents the line that the graph will not cross because x can't equal that value. So look at the denominator now. Set it equal to 0. What value can x not be? X cannot equal negative 4. So that's the asymptote, when x does equal negative 4. So that's step 3. You could plot the x-intercept. You could do this dashed line to represent the vertical asymptote. What do you think's next? Yeah, you guessed it, horizontal asymptote. So step 4, find the horizontal asymptote. Now, there's a bunch of rules for this. I'll explain it to you here. So you remember degrees of a polynomial? So the degree of this polynomial is the size of the biggest exponent in the variable, right? So look at the polynomial on top here. It's degree 1. Polynomial on the bottom is degree 1 as well. Let me show you some more examples. This is degree 1. Look at the biggest exponent on the variable. Degree 1 on top, degree 1 on bottom. Let me see if I have another example. Oh, here we go. So this example has degree 1 on top, but a degree 2. You see that? Degree 2 on bottom. And so there's rules for finding the horizontal asymptote. If the degree of the thing on top, so P, remember P is the polynomial on the top. If the degree of the top polynomial is bigger than the degree on the bottom, then you will not have a horizontal asymptote. There's 3 cases. Case 2, you could have the degree on the top being smaller than the degree on the bottom. And if that's the case, then the horizontal asymptote is going to be y equals 0, which is the x-axis, right? And then lastly, if the degrees equal the same thing, so like if the degree on top equals the same thing as the degree on bottom, then what you have to do is you have to look at the leading coefficient of the polynomials. And the asymptote will be whatever the lead coefficient is of P of x over divided by whatever the lead coefficient is of Q of x. Let me show you an example for each. So next we got to find the horizontal asymptote. Let's take a look at this problem here. So we need to look at the degree. This is degree 1 over degree 1. That means their degrees are equal. And so here we go. Since the degrees are equal, we need to figure out what's the leading coefficient of P of x. Leading coefficient's the number in front of the variable. So the number in front of x is 1. Do you see it? No, because it's just 1. So this lead co is 1. The bottom's polynomial's lead coefficient's also 1. So what we have is y equals 1 over 1, which is just 1. So the horizontal asymptote is y equals 1. That's why in this problem we have a dashed line where y equals 1, and that's the horizontal asymptote. All right, let's close this one out. Let's close this one out, and then we'll do more examples. Lastly, you have to identify any holes in the function. So a hole in the function is a spot, and let me show you an example if we have one here. Okay, here. Take a look at this hole right here. A hole in the function is a spot where that value doesn't exist. So take a look at this hole. What is the x value there? Let's see. 1, 2, 3, 4, 5. When x is negative 5, well, let me put it this way. X cannot equal negative 5. And so this is not an asymptote, but this is a value that we have to take out. That's why it's a hole in the function. X can't equal negative 5. And that's because if x did equal negative 5, here, so this is the polynomial, and this is it in factored form, right? So there's 2 values that x can't equal. You've got the value of at negative 4, x can't equal negative 4, x can't equal negative 5. Well, a hole happens when you have a excluded value that is canceled out of your fraction. So notice this, we could cancel the x plus 5s and you get 1 over x plus 4. Look, we canceled out a factor that we still need to consider the value that is not allowed. Does that make sense? And so since we canceled this value out, that is going to produce a hole where x equals negative 5. And so that's a hole on this graph. Now we would have to find the y value by plugging in negative 5 into the original and solving, but that's just a demonstration on what a hole is. So let me go back to the top and just recap with you. First, you want to simplify. Then you want to find the x-intercept by setting the numerator equal to 0. Then you want to find vertical asymptotes setting the denominator equal to 0. Then you want to find horizontal asymptotes following these rules for these 3 cases, depending on the degrees of the polynomial. Lastly, you want to identify any holes in the function. Holes occur when you cancel out like factors. And so here you can see here, a hole is a point at which there's a break in the graph. A hole occurs when there is a common factor that you've canceled out. You have to find the x-coordinate, and then you have to, to find the x-coordinates. We found the x-coordinate, but then you have to find the y-coordinate by substituting that x value into the simplified function. So that's what a hole is. Let's go ahead and do this problem that has a hole from the top, just so you can see what's going on here. Where What's the one that we were just looking at? Here it is. Okay, step 1, simplify. So to simplify, we could factor the bottom. Factors in x plus 4 times x plus 5. Step 2, find the x-intercept. So the x-intercepts when we set the numerator equal to 0. Numerator is x plus 5. So when x equals negative 5, the top will equal 0 and y will equal 0. So our x-intercept, okay. Actually, there is no x-intercept because x can't equal negative 5. So, there's a bunch of rules to this. If you factor it out, then it's not going to be the x-intercept because x can't equal negative 5. I hope that makes sense. All right. So, because it factors out, there is no x-intercept. Next, vertical asymptote. Well, that's the value that x can't equal. Well, there's two values that x can't equal. But since the x equals negative 5 one cancels out, we got to go with the x equals negative 4 for our vertical asymptote. So this line, this dashed line, is where x equals negative 4. So we would simplify this. We would first graph this vertical asymptote where x equals negative 4. Then we would find the horizontal asymptote. Before, you wouldn't have graphed this yet. I'm just walking you through it. Horizontal asymptote. So go back to the original. Look at the degree on the top. Now, I got to stress this. Go back to the original for this, okay? Degree on top is 1. Degree on bottom is 2. And so let's look at our rules here. If the degree on the top is bigger than the degree on the bottom, that's not what we have. We've got 1 over 2, right? Okay, so 1 over 2, this is the scenario we have. P is bigger than Q, its degree, which means that the horizontal asymptote is y equals 0. Okay, where are we? Here we go. This is it. All right, y equals 0. So that's our other asymptote. Now, after you drew the vertical and horizontal asymptote, then you should know where these curves, what quadrants these curves are going to be in, based on if the a value is positive or negative. So here, a is positive. Look, we've got a positive 1 on top, which means that the curves will be in quadrant 1 and 3. And so we can draw the graph here. First, I'd probably find the hole before I drew the graph. So to find the hole, you take the value that x can't equal, and let me do this one for you, actually. We got 1 over x plus 4. Okay. I'm going to take the value that x can't equal, right? So x can't equal negative 5 because I canceled it out, right? We got an x plus 5 that I canceled out. X plus 5. And so I need to find the y value that goes along with that because I need to show that that's a hole in my graph. It's a break in my graph. So when I plug in a negative 5 for x, I get 1 over, and do this in the simplified fraction after you cancel, okay? Okay, let's see. Bam, I plug in a negative 5. I got negative 5 plus 4. That's 1 over negative 1, which is negative 1. So this point here is a hole on my graph, and I need to show that it's a hole. So I'm going to go to negative 5. Okay, negative 5, negative 1. There it is. And now it's a hole on my graph. Once you do all that, go ahead and do your smooth curves, and you're done graphing. Then you just need to write down all the stuff you found. And so the hole is negative 5, negative 1. What about the domain? Well, you need to say the values that x can't equal. X won't equal negative 5, and it won't equal negative 4. Then you need to say the range, the values that y won't equal. Since there's an asymptote here where y is 0, y won't equal 0. And because there's a hole here, y won't equal negative 1. And so the domain and range relates to all this information that you wrote down. Notice the domain is related to the vertical asymptote. X can't equal the vertical asymptote, and x can't equal this x coordinate on the hole. Also, look at the range. The range is related to the horizontal asymptote. Y can't equal 0, because that's a horizontal asymptote. And then take the coordinate and the y value on the hole. Y can't equal that either. And so that's pretty much you graphing this whole thing, all right? Now, let's see. In some cases, like let's look at this one. In some cases, you actually won't have any curves, and I'll show you why. Step one, we need to simplify, right? So we factor this. We got x minus 1 times x plus 1, and it looks like we can cancel out these x minus 1s. And this is what we get, simplified version, x plus 1. If you simplify it and after canceling you do not have a fraction, what that means is that your graph is going to look like a line. Or if this was a quadratic, your graph would end up looking like a parabola. Basically, if you don't have a fraction with a variable in the denominator after you simplified, right, like this, if you do not have a variable in the denominator, then your graph won't look like this. It's going to end up looking like whatever the simplified version is. And since this simplified version is a linear function, it's going to look like a line. Anyways, you still have to find the holes. Now, a question that you might be asking is, well, what about the x-intercept, right? Well, okay. Well, let's see. The x-intercept is a value that you can get the top to equal 0, right? And so after you've canceled out these x minus 1s, this here is the top, so to speak. And look, if x was negative 1, it would equal 0, right? And so that's where it crosses the graph when x is negative 1. So that's your x-intercept. Your vertical asymptote, horizontal asymptote. Vertical asymptote is when the denominator equals 0, but look, the denominator canceled out, and so there is no vertical asymptote. Horizontal asymptote, well, let's take a look here. Horizontal asymptote. If the degree of P is bigger than the degree of Q, okay? Yeah, look, the degree on top is bigger than the degree on the bottom, which means there is no horizontal asymptote, none. Okay, good. Now, our hole, we need to find our hole. Well, the hole is the value that we canceled out, where x is 1. Plug in x equals 1 for your simplified version. And so 1 plus 1 is 2. And so when y is 2, or when x is 1, y is 2, that's the hole, okay? Notice those are the two values that are restricted in the domain and range. So yeah, that was a good example. Let's take a look at this other type. So you could have some weird stuff like this. This will happen when you have two vertical asymptotes. And yes, that can happen. I'll show you why. Step one, factor, right? Factor top, factor bottom. So this top here factors into that. The bottom factors into that, okay? Let's see. Nothing cancels, right? And so let's go back to, okay, well, how do we find our x-intercept then? Well, the x-intercept is when, you know what, let me do this on paper so you can see it. I got 2x plus 1 times x minus 1 all over x minus 4 times x plus 3. All right. So the x-intercept is when you have 0 in the numerator. So for each of these factors, there's an x value that'll give you a 0. And how do you find that? Well, you just take this factor, you set it equal to 0, and you solve. 2x plus 1, equals 0, subtract 1, divide by 2. So when x equals negative 1/2, you have you have an x-intercept. That's when y will equal 0. So that's one of your x-intercepts. And this one, when x equals 1, now how do you find that? Well, you just take the factor, set it equal to 0, and solve. So when x is 1, y will also equal 0. So there's two x-intercepts. Let's see. Oh, and here they are. Two x-intercepts, negative 0.50, that's negative half, and there it is. And 1, 0, and there it is. There's two x-intercepts. What about our vertical asymptotes? Well, the vertical asymptote is the value for x that makes the denominator equal 0, right? So again, take the factor, set it equal to 0, and solve. But here you can see if x is 4, that's a vertical asymptote. When x is negative 3, that's a vertical asymptote. And here we've drawn our vertical asymptotes. When you have two vertical asymptotes, you always have a graph that ends up looking like sort of like a parabola in the middle. It might open up, it might open down. And then you'll have these two little curves off to the side like that. So what I want you to do is I just want you to find all your vertical asymptotes, horizontal asymptotes, find the hole. In this case, there's no hole because we didn't cancel anything out. Oh, let's talk horizontal asymptote. Looks like they have the equal degree, right? So when the degrees are equal, you look at the lead coefficient. So here the lead coefficient is 2, and here it's 1. So y equals 2 over 1. Your asymptote is 2 over 1 is 2. And that's why here we have our horizontal asymptote. So what I suggest is you can use Desmos to see what the end result will look like of the graph, or you can plug in values in these quadrants. Now look, our asymptotes divided our graph into like 6 quadrants. Here's one quadrant, here's a second quadrant, here's a third quadrant, 4, 5, 6. Do you see it? And so I'd probably start with the middle, and like you could just, well, actually here, since we already found these values, we found the x-intercepts. Since you found the x-intercepts, you know that this part of the graph has to stay in this quadrant, which means there's not going to be anything in this quadrant. Do you see it? And so because, let's see, because this is our asymptote here, the graph won't be going past the asymptote. So you could use that information to know that this thing goes down. And you can just make it ride closer and closer to the asymptote line. What about this one? Well, all you really need is 1 point in this quadrant, right? So pick an x value that's on this side of this vertical asymptote and find the point. Like, let's see. 1, 2, 3, 4. Okay. When x is -4. So you could plug that into simplified or into this value. When x is -4, let's see. We got -5 here. We got -8 plus 1, that's -7. -7 times -5, that's +35 over, let's see, when x is -4, this would be -8 times a -1, which would be a +8, +8 over 35. It's some weird decimal, right? But you can find that. And here you can find that value. So if you find a point that's in one of these quadrants, the part of the graph has to either be in this quadrant or in this one. It can't be in both. And so once you find that point, you could probably just do the graph from there. You know what the graph looks like, the shape of it. Okay, I hope that makes sense. All right, sorry for the long video. Hope all is well. Bye-bye now.